All right, so cylindrical and spherical coordinates, section 11.7. Cylindrical coordinates are exactly like polar coordinates, just with a z tacked onto it. So let's begin by reviewing polar coordinates. If I have a point in the plane, so here's my xy plane, and say it's this point right here, we'll call that the point xy. I can describe that point, instead of just xy, I can describe it as the distance that point is from the origin, r, or the radius, and the angle made by that radius with the positive x-axis. So this point can also be described simply as r theta, where r is equal to, back the train up, x is equal to r cosine theta, y is equal to r sine theta, and r squared is equal to x squared plus y squared, and tangent of theta is equal to y over x. Okay. So the idea with cylindrical coordinates is we're going to use that same concept to get us into the correct position relative to x and y. Then we'll just move vertically to achieve the appropriate z direction. So for example, if I'm in R3, here we go, so there's my x, y, and z. I might have a point, say here, say octant 1, right up here. Okay. Then in order to find this point, the way we're going to describe it is we're going to say, okay, well, it has a position in the xy plane. Okay. So that position is given by theta and r. So that puts us in the correct position in the xy plane. Then from there, we're going to move vertically up to the point in the, up to the appropriate z value to find that point in three-dimensional space. So that's what's going on here. Okay, so let's go ahead and write all that down. We have cylindrical coordinates. They are of the form r theta z. So literally it's like polar coordinates with a z tacked on for that third coordinate. And the conversions for these are going to be exactly the same formulas as what I wrote above, plus the z. So we have x is equal to r cosine theta, we have y equal to r sine theta, we have tangent of theta equal to y over z, we have r squared equal to x squared plus y squared. The only difference is now we have z, which is z. So it's the exact same value in both rectangular coordinates and the cylindrical coordinates. So that's going to, let's do some examples where we convert between the two different types. So example, let's convert from rectangular, which are the x, y, z coordinates, to cylindrical, r theta z. All right, so the point is 1, -1, 2. So that's our x, y, and z. Okay, so we need to figure out then what is r, what is theta, and what is z. Well, z is the easy one because there's no conversion. Z is just z, so in this case z is 2. R is going to be given by r squared equal to x squared plus y squared, which is 1 squared plus -1 squared, which is 2. So r is equal to root 2. Now we're going to use the convention that r is going to be a positive number since we are dealing with a radius. It is of course possible to describe r as a negative number, just meaning we're going to move in the opposite direction of the given angle. However, for our purposes, we're going to keep r positive. So that's square root of 2. Now to find theta, we're going to use tangent of theta is equal to y over x. Let's see, x. So that's -1 over 1. Or -1. All right. So one thing to keep in mind is that theta is going to be an angle between 0 and 2 pi. So we need theta between 0 and 2 pi. That 0 looks kind of like a theta. 0 and 2 pi. All right. The second thing to keep in mind is that tangent has a period of pi, not 2 pi. So tangent any given value of the tangent is going to occur twice between 0 and 2 pi. So we're going to identify both of those angles, and then we're going to figure out which one is the correct one. All right, so you can do this by using the unit circle, putting it in your calculator, what have you. The inverse tangent of -1, that's our theta, right? So we have tangent theta is -1, so we need the inverse tangent of -1. The calculator is going to give us negative pi over 4 because the range of the inverse tangent is going to be negative pi over 2 to pi over 2. Okay, so that's what the calculator spit out at us. So we're going to find the angles that are between 0 and 2 pi by adding pi. So theta could be negative pi over 4 plus pi, or theta could be negative pi over 4 plus 2 pi. Okay, so we add 1 pi to get to the first one, and then 2 pi to get to the next one. So theta could be 3 pi over 4, or theta could be 7 pi over 4. So how do you know which one? Well, the answer is go back to the original point in rectangular coordinates. So in rectangular coordinates, just looking at x and y, we have the point 1, -1. That's fourth quadrant. So the angle here, oops, missed. So the angle here is going to be a fourth quadrant angle. That's 7 pi over 4. That's how we know that that's the correct angle. So the angle we need is 7 pi over 4. So now we have it. We have our entire point. It is root 2, 7 pi over 4, 2. That is our theta z. Okay, so now let's go the other direction. Now let's convert from cylindrical to rectangular. And I think you'll find this one to be a little bit easier to do. So convert from cylindrical to rectangular. All right, so here's our point, 2 pi over 3, -3. So that's r theta z. Okay, so we need to find x, y, z. Z, of course, is the easiest one. We don't have to do any converting. And x is r sine theta, r cosine theta, and y is r sine theta. So these are pretty easy for us to do. We can just go ahead and pop these numbers in. We have 2 cosine of pi over 3, and r sine theta will be 2 sine of pi over 3. Cosine of pi over 3 is 1/2, so this is 2 times 1/2. Sine of pi over 3 is root 3 over 2, so this will be 2 times root 3 over 2. So that's going to come out to be 1 and square root of 3. And so our point in rectangular form is going to be 1 square root of 3, -3. That's our x, y, z. All right, so now we're going to use these conversions to convert between rectangular and cylindrical form of an equation. So let's convert between cylindrical and rectangular form. We're going to use exactly the same formulas, the same identities that we've been using. So nothing new going on there. So let me just give you an example. X squared plus y squared is equal to 8x. There you go. So how do you know what you're converting to? Well, the key is what were you given? We've got x squared plus y squared is equal to 8x. Clearly that's in rectangular form because there are no r's, there are no thetas. So this we need to convert to cylindrical form. So we're going to do that. The first thing you might notice is we have an x squared plus y squared. Automatically that's x squared, r squared. Comes right out of the Pythagorean theorem. And then we have an x. So that's going to be r cosine of theta. Okay, so we make these substitutions. So we have r squared is equal to 8 times r cosine of theta. Okay, so it can be tempting to just stop right here. However, with the textbook, they do require us to go a step further, especially when we only have r's and thetas in our equation. So what we're going to do is we're going to get everything on one side, r squared minus 8r cosine of theta equal to 0. Factor out the r. R is equal to r minus 8 cosine of theta equal to 0. Okay, so r equal to 0 is clearly a solution to this equation. However, we find that there is a theta that allows r minus 8 cosine theta to be equal to 0 as well. So we don't lose anything by dividing the r. So let's go ahead and divide that r, and we get r minus 8 cosine of theta is equal to 0. Then we have r is equal to 8 cosine of theta. Okay, so I just want to give you a heads up here. Is there anything wrong with stopping above? No, not necessarily. But this is nice because now we can completely express r as a function of theta, whereas earlier we didn't have that because r was being squared. All right, so let's do another example where we go the other direction. So how about r squared cosine of 2 theta plus z squared plus 1 equal to 0? Okay. All right, so the first thing you might notice is there's a cosine of 2 theta in here, and we don't have any kind of conversions for double angles. But we do have a lot of trig identities at our disposal that we can use. So we're going to apply the trig identity. Let me write this down. So we're going to use the fact that cosine of 2, that is really dark. I don't know how well that shows up for y'all, but it is too dark for me. So I'm going to get rid of that. Let's try green here. Okay, so we're going to use the identity cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta. All right, so we can use this identity to turn this into something that we can work with a little bit easier. So this becomes r squared times cosine squared of theta minus sine squared of theta plus z squared plus 1 equal to 0. Distribute the r squared. Okay, so r cosine theta is x, so r squared cosine squared theta is x squared minus r squared sine squared is y squared plus z squared plus 1 is equal to 0. And there we have it. If we wanted to, we could move the constant to the other side, but it's not really necessary. Okay, so one more example I wanted to show you. What if I had something like this, r equal to 3 cosine of theta? Okay. We've got a little bit of difficulty here because we know that r squared is x squared plus y squared. We know that r cosine theta is equal to x, but cosine theta by itself, we really don't have anything for. Same thing with r by itself. We don't really have anything for that. So a very common tactic to use here is to simply multiply both sides of the equation by r. Then what we get is r squared equal to 3 times r times cosine of theta. Now I've got r cosine theta, which we know is x, and r squared, which we know is x squared plus y squared. So this gives us x squared plus y squared is equal to 3x, and done. That's it. That's what we've got. Okay? All right, so multiplying by an r on both sides of an equation is a common way to get it into a form that we need. So if we're not handed something already containing all of the beautiful, elements of our conversion equations, we can always kind of manipulate it to create it and make it that way. All right, so now on to spherical coordinates. Spherical coordinates. Spherical coordinates are very different. I say that. They're very different in that they're approaching the point from a very different perspective. Okay, so again, let's suppose I have got a point in 3 space. 3, z, there we go. So suppose I have this point right here, okay? And if I were to draw the lines down and show you kind of the corresponding position in the xy plane, this is what we would get. It would kind of be here, right? So it would kind of be this y value, this x value, and then up to whatever this z value is here. Okay. However, we're not going to describe this one in terms of polar coordinates, cylindrical coordinates. We're going to look at this one more as its absolute distance from the origin. So how far is that point from the origin, just in space? Okay. And we can't call it r because r is the radius as if we were get another color here, right? This would be r just to the kind of the image of that point in the xy plane. So we can't call this one r. What we call that distance is rho. Looks like a pretty p. So this is the Greek letter rho, R-H-O, right? Rho. And that's going to give us our absolute distance from the origin, okay? Then we've got a couple of different angles that we're dealing with. The first angle is still theta. Theta has not changed. And theta is still going to be the distance that our image creates, the image of our point creates in the xy plane with the positive x-axis. So that is still going to be our theta, same theta. Now we have something different though. We've got another angle. So we're going to talk about this one here. This angle from the positive z-axis is phi. P-H-I. It is also appropriate to call that phi, or phi. I will typically refer to it as phi. Okay, so to walk you through kind of the way we're finding this, the point that we're given is rho theta phi. There, got it out. Rho theta phi. Okay, and the way we're finding this point is we're going to extend out. You might think of it in this way: extend out rho along the positive x-axis. Just come out on rho. Let me draw a picture so I can kind of talk you through what I'm thinking. Okay, so we're going to come out rho on the positive x-axis. Okay, so we come out rho. And then from there, we're going to swing out in the xy plane. We're going to swing out theta. Okay, then we are going to measure from the z-axis, we are going to measure down phi. So from here, we're going to come down phi. So I'm going to raise this up, swing it up, until I get phi. Oh, that is a terrible drawing. Let me try that again. I'm trying to go straight up until I have the angle phi that I'm looking for. So I'm still creating this angle theta. I still have rho as my distance between, and phi is my angle here. So that's kind of how I always think about it. I always kind of think about it as walking out rho on the x-axis, swinging around through the xy plane to the appropriate angle theta, and then swinging up until I reach the angle needed with the z-axis. Okay, now with spherical coordinates, we have conversions directly to rectangular coordinates and directly to cylindrical coordinates. It is not necessary to have both of those necessarily at your disposal, if that makes sense. It's good to be able to just do them. However, you're working off of a 4x6 index card for the exam. So as long as you can get from one to the other to the other. So for example, if you can go from rectangular to spherical and rectangular to cylindrical and back again, you can go from spherical to cylindrical via rectangular coordinates. So you can always do one conversion and do the next conversion if you need to. However, we do have direct links between all three types. So let's go ahead and write those down. Okay. All right, so something to keep in mind, I did not mention this, but let me do it now. We need rho to be positive. We're going to, just like we did with the r, we want that to be a positive value for convention's sake so that we are able to keep it very clean and straightforward what we're working with. Let's go ahead and write those conversions down. So conversions. If you're going from spherical to rectangular, okay, you'll primarily be using x equal to rho sine phi cosine of theta, y equal to rho sine phi sine theta, and z equal to rho cosine of phi. Okay. If you're going the other direction, rectangular to spherical, all right, we have rho squared is equal to x squared plus y squared plus z squared. Okay, so just again that extension into third dimension. Rho then would be the square root of x squared plus y squared plus z squared. So that might be more convenient if we need to use that. We have tangent of theta is y over z, and we have cosine of phi I got to work on that circle. Cosine of phi, there we go, is equal to z over rho. Or you could also write that then as z over the square root of x squared plus y squared plus z squared. Okay. And then if we're going from spherical to cylindrical, okay, we would use these. We have r squared is equal to rho squared sine squared of phi. Theta is, of course, equal to theta, which is nice. And z is equal to rho cosine phi. Okay. And if you're going in the reverse direction, cylindrical to spherical, all right, then we have rho equal to the square root of r squared plus z squared. Theta, of course, is theta. And phi is equal to the arc cosine of z over the square root of r squared plus z squared. Okay. So again, if you find one of these methods more difficult than the other, use the one that's easier for you and then convert from there to the one you're after. Okay, so let's see these guys in action. Let's convert to cylindrical. This point, rho theta phi equal to 9 pi over 4 pi. Okay, so we're going to cylindrical. So what we're looking for is r theta z. This is what we're looking for. So we need to know what is r, what is theta, what is z. Well, theta is theta, so that's nice. So theta is simply pi over 4. Okay, and our formula for r is r squared is equal to rho squared sine squared phi. Okay, so plugging in those values, we get 9 squared times sine squared of pi. But of course, sine of pi is 0, so that's just 0, so r is 0. And then for z, our conversion formula there is z is equal to rho cosine of phi. Rho is 9, cosine of phi is pi. Cosine of pi is -1, so this is 9 times -1, or -9, so there's z. So our point in cylindrical coordinates is given by 0, pi over 4, -9. Okay, and to keep things consistent, let's go ahead and convert an equation from rectangular form to spherical form. So convert the rectangular equation to a spherical form. So we have x squared plus y squared plus z squared minus 9z is equal to 0. Okay, well, x squared plus y squared plus z squared is rho squared. And then z is going to be equal to rho cosine of phi. Rho cosine of phi. So this becomes rho squared minus 9 rho cosine of phi equal to 0. All right. So in the same line of thought as before, we can factor out a rho here and divide that rho out without losing our 0 factor. So we can divide rho away to get rho minus 9 cosine of phi equal to 0, or rho is equal to 9 cosine of phi. Again, if there's something that we're given that's really not in the form that we need it in, it doesn't have any of the elements from our conversion equations, we can always multiply or manipulate the equations as we are able to do in order to obtain forms that we can work with. Okay, so that's it for this one. As always, if you have any questions, please let me know. If you need supplemental information with better drawings, I highly recommend you check out Khan Academy's video on these, okay? Have a good one.